This is the story of numbers, almost all of them, where they came from, who first reached for them, and how a few scratches on a piece of old bone slowly grew into the whole vast machinery we now use to weigh and count and price and measure the entire world. There is a little word hiding in the title of all this. The word is almost, and I want you to hold on to it gently, because it is going to follow us the whole way. Like a quiet promise that there is always one stranger number waiting just past the edge of the page. But for now, there is no rush at all. Settle in, get comfortable. You don't have to remember any of this, or follow it perfectly, or stay awake until the end. There is nowhere you need to be tonight, and nothing you need to do but breathe slowly and let these old ideas drift over you like weather. Let's start with something that feels almost too obvious to say out loud. Numbers are everywhere. The time on the clock, the page of a book, the coins in a pocket, the floors in a building, the years of your own life. They feel as natural as the air, as if they were simply lying around in the world all along, waiting to be picked up, like stones on a beach. And here's the strange part. They weren't. Nobody ever found a number lying on the ground. Somebody, or rather a great many somebodies, spread across an almost unimaginable stretch of time, had to invent them. I know that sounds odd. Of course, numbers are real. You might think, 3 is 3. But let me try to convince you that the thing you're so sure about is one of the most quietly astonishing inventions our species ever made. Start with an animal. Imagine you're holding out a handful of stones to a crow. And crows, by the way, are genuinely clever creatures. Show a crow 1 stone, then 2, then 3, and something in that small dark mind keeps up. The crow can tell the difference between a few things and a few more things. Men animals can. A lioness seems to hear the difference between 1 roar and several roars in the dark. A newborn baby, only a few hours old, will stare longer when the number of dots in front of it suddenly changes. So there is something in there, deep and ancient, that notices amounts, but it is blurry. It is a feeling, not a count. Show that same crow 7 stones, then 8, and the difference simply dissolves. The crow has a sense of a little and a lot, and almost nothing in between. And honestly, so do you. Look at 3 dots on a wall and you just know, instantly, without counting, that there are 3. Look at 4, and you can still mostly feel it. But look at a scattered handful of, say, 17 dots, and that instant knowing vanishes. You have to do something. You have to count. That dividing line, that little cliff edge somewhere around 3 or 4 where seeing becomes counting, is roughly where the animal mind stops and where the human adventure begins. So here is the first real character in our story. And we don't know their name. We will never know their name. Picture this. It is somewhere in the south of Africa, in a range of hills we now call the Lubombo Mountains. The light is low. Someone is sitting with a small length of bone in their hands, the leg bone of a baboon, and they are cutting marks into it. Not a picture, not a decoration, as far as anyone can tell. Just a line, and then another line, and another. 29 small notches, cut carefully, one beside the next. We don't know exactly how old it is. The dating is argued about, and you'll see figures anywhere from 35,000 to 44,000 years. But take the larger number for a moment and just feel the size of it. 44,000 years ago, there were no cities. There was no farming, no writing, no metal. The last ice age had not even ended. And in that world, somebody sat down and made a tally. That many, and no more than that. We call this little object the Lubombo bone. And it is one of the oldest mathematical objects we have ever found. Let that hang in the air for a second. There is another one, younger, from much further north, near a lake in what is now the Democratic Republic of the Congo. We call it the Ishango bone, and it is maybe 20,000 years old. This one is stranger. Its notches come in deliberate groups. And people have spent decades arguing about whether those groups hide something clever. Some early game with doubling, or with odd numbers, or even with primes. Maybe they do. Maybe we are seeing patterns in the dark that were never really there. Nobody knows for certain. And I think the honest uncertainty is part of the beauty of it. Either way, the simple fact remains. Long before history began, human beings were already keeping count, one careful scratch at a time. Now I want to slow all the way down, because we are about to walk straight into the single deepest idea in this entire story. And it is so simple that it usually slips right past us. That person cutting notches into the Lubombo bone was almost certainly counting something. Days, maybe, or kills, or moons, or people, or animals. One scratch for each real thing, and that is a marvel on its own. But it is not yet the truly strange leap. The truly strange leap is the one that happens when those scratches stop being about any particular thing at all. Think about the word 3. When you say it, you are not talking about 3 sheep, or 3 stones, or 3 stars. You are talking about something that all of those have in common, and nothing else. Threeness. The bare fact of there being that many, lifted clean away from any actual objects. A word like 3 is a kind of coat hanger. You can hang 3 sheep on it. You can take them down and hang 3 mountains on it instead. Or 3 sounds. Or 3 sorrows. The hanger doesn't care what you put on it. It holds the shape. And the shape is all that matters. And here's what gets me. Every single time. There is no such thing as 3 anywhere in the universe. You can walk outside and find 3 apples. You can find 3 birds on a wire, 3 cracks in the pavement, 3 grey hairs. But you cannot, anywhere, in any forest, or on any mountain, or at the bottom of any sea, Find 3, just 3, by itself. With nothing being 3, it isn't a thing you can touch, or point at, or stub your toe on. It is a pure idea. And our ancestors had to drag that idea up out of nothing, with their bare minds, over tens of thousands of years. Say that slowly to yourself. You cannot find 3. This is the leap from 3 sheep, which you can see, to plain 3, which you cannot, from counting actual things in front of you, to holding the number itself, weightless, in your head, where it can be carried over to anything. And it is so easy to miss how enormous that jump really is, because every one of us made it as a small child, and then forgot we ever had to. Which brings me to the part of all this that I find almost unbearably lovely. Every single time a child learns to count, they are quietly re-walking a road that took our whole species tens of thousands of years to build. A 2-year-old saying 1, 2, 3 while climbing the stairs is, without the faintest idea of it, repeating one of the great intellectual journeys in the history of life on this planet. They are reinventing the abstraction. They are pulling 3 loose from all the 3s in the world, exactly the way some unnamed genius did, by firelight, before the cities, before the wheel, before almost everything. Just sit in that warmth for a moment before we move on. Once that leap is made, once you have numbers floating free of the things they count, you can start to do something new with them. You can build, you can write them down, and pass them on, and stack them into systems. And here is where our one quiet story splits into many. Because different peoples, all over the world, each built their own machinery for holding numbers. And they did not all build it the same way. Let me take you to the flat land between 2 rivers, in what is now Iraq. Around 5,000 years ago, the Sumerians, and after them, the Babylonians, were keeping records on wet clay, pressing little wedge-shaped marks into it with a cut reed. And they did something that should feel completely bizarre to us, and yet secretly still rules your daily life. They counted in 60s. We count in 10s. Almost certainly because we happen to have 10 fingers. The number 10 feels obvious to us, for no deeper reason than the shape of our own hands. But the Babylonians built their whole system around the number 60, and it sounds clumsy until you notice why it is. In some ways, cleverer than ours. 60 can be split cleanly so many ways. Into halves, into thirds, into quarters, into fifths, into sixths. It shares itself out beautifully. And here's the thing that still gives me a small shiver. That choice never went away. Look at a clock. 60 seconds in a minute. 60 minutes in an hour. Look at a circle, sliced into 360 degrees. Every time you check the time, every time you turn a corner and someone says you turned 90 degrees, you are using a number system that was set down in clay by scribes who have been dust for 40 centuries. They are still, in a sensor, in the room with you. I think about that more than I'd like to admit. Now, sail west to the Nile. The Egyptians counted in tens, like us. But they wrote their numbers as little pictures, a single stroke for one, like a tally mark surviving into the age of writing. A shape like a bent heel bone for 10, a coil of rope for 100, a lotus flower for 1,000, and, my favorite, a tiny figure of a man with both arms flung up toward the sky, as if in astonishment, to mean 1,000,000. Imagine that. To write the largest number you could easily name. You drew a person who looks utterly amazed. There is something so human in that the symbol for a vast amount was just a little astonished man. We know a great deal about how they did their arithmetic because of a single document, copied out by a scribe named Ahmes. More than 3,500 years ago, he tells us, right at the start, that he is only copying older writings from a time already ancient to him. So even our oldest math homework was a copy of someone else's even older math homework. The story was already long before anyone thought to write it down. And then, on the far side of the world, with no possible contact, the Maya in Central America did the same deep thing all over again. In their own way, they counted in 20s, fingers and toes together, and they built a calendar of staggering precision. And here is one of those moments that makes the hair stand up on the back of my neck, because it tells you these ideas were somehow in the air, waiting to be found by anyone who looked hard enough. The Maya, all alone, reached something that almost no one else in the ancient world had reached. They had a symbol for nothing, a little mark shaped like a shell, sitting in their numbers to hold an empty place. They had stumbled onto an idea so subtle that the rest of the world would struggle with it for thousands of years. But, and this is the quiet tragedy in it, that Mayan discovery stayed locked inside the Americas. It never traveled. It never joined the main current of the story we are following. The long river that runs from those two rivers in Iraq, through Egypt, and onward into the wider world, and along that great central river of human counting, in nearly every system we have met tonight, something was missing. Ahole, right at the heart of the numbers. So let's gather it all up softly before we close this first stretch of the road. We started with a crow that can tell 2 from 3, but not 8 from 9. We sat beside someone in the African dusk, cutting 29 careful notches into a baboon's bone. 40,000 years before the pyramids, we watched our whole species, and every child since, to perform the same impossible magic trick, lifting the bare idea of 3 up out of every real 3 in the world. And we watched scribes in clay and stone and papyrus, on 3 different continents, each build a beautiful, strange machine for holding numbers. 60s in Iraq, 10s by the Nile, 20s in the jungle. A whole civilization, in the end, balanced on top of a single idea that our ancestors had to fight to even imagine. The simple, weightless, invisible thought that a number can exist all on its own, I find that genuinely moving. Out of all the things human beings have built, the cathedrals and the engines and the songs, one of the very first was this: the quiet realization that how many is a thing you can hold and keep and pass to your children. But there was one number that almost none of these early counters ever thought to write down. A number sitting right there in plain sight, in the empty hand, in the missing day, in the place where the tally had not yet begun, and it left them all stuck on the same impossible little question. How on earth do you make a mark for the thing that isn't there? Because that missing number, the one that stands for nothing at all, was about to cause more trouble and more wonder than any number that came before it. So, let's go looking for it. The missing number. The one that almost everybody, across almost all of history, somehow never quite managed to write down. And the strange thing, the thing that makes this whole chapter feel a little like a detective story told in a whisper, is that the number was never actually hidden. It was sitting in plain view the entire time. In the empty hand, in the day, nothing happened. In the gap between having some and having none, the hard part was never finding it. The hard part was admitting it was there. Come back with me to those scribes in the land between two rivers, pressing wedges into clay. Their counting was clever, but it had a quiet flaw. And you can feel it if you imagine a very old kind of calculator. Picture an abacus, a wooden frame with beads sliding along rods. Each rod is a column. Ones on this rod, tens on the next, hundreds on the next. Now picture a number where one of those middle rods is simply empty, no beads at all. You and I would write a small mark there to say nothing in this column. Keep going. But what if you had no such mark? Then the empty rod just looks like a smaller gap, or no gap. And suddenly, the number written down could mean a dozen different things. That was the Babylonians' problem. For a long time, they just left a blank space where a column was empty. And a blank space is a terrible thing to trust. So eventually, after centuries, they invented a little symbol to drop into that hole. A faithful little nothing, whose only job was to say, "This place is empty." But it still counts as a place, and that was a real step forward. But it was not yet what we are hunting for. And here's the thing. A placeholder like that isn't really a number at all. It's closer to a mark of punctuation. A small separator that helps you read the other numbers correctly. Like the space between two words. The Babylonians never thought to add it to anything, or take it away from anything. They wouldn't have dreamed of it. The truly difficult leap, the one that took humanity another 1,000 years, wasn't drawing the symbol. It was letting nothing have a personality. It was deciding that emptiness itself could be a number you do arithmetic with. A number that sits in the lineup right next to 1 and 2 and 3, and pulls its weight. That leap happened in India, and I want to slow down and introduce you to the man who, more than anyone, made it. Because he is exactly the kind of human the history books tend to flatten into a date. His name was Brahmagupta. He was born around the year 598 in a town called Binmal. in the northwest of what is now India. And he grew up to run the great astronomical observatory at Ujjain, which in his day was something like the beating heart of mathematics and stargazing for the whole region. And he was, by every account we have, a little bit of a difficult man, brilliant, and he knew it. He wrote his mathematics in verse, in flowing Sanskrit poetry, which is lovely. But he also used that poetry to take sharp, sarcastic swings at rival astronomers he thought were fools. You read his work and you can almost hear him muttering. This guy was not gentle with people he disagreed with. But in the year 628, in a long work whose title means something like the correctly established teaching of Brahma, he did something quietly world-changing. He wrote down the rules, the actual rules for how this strange new number, the one for nothing, behaves. If you add nothing to a quantity, he said, the quantity is unchanged. If you subtract a thing from itself, what remains is this nothing. He gave it a place in arithmetic. He let it add and subtract and sit in equations like any other number. For the first time, in writing, nothing was allowed to be something. Let me say that again, slowly, because it's easy to skate over. A human being looked at absence, at the void, at the empty hand, and said, that, too, is a number. I find that genuinely staggering. It is one of the most abstract thoughts anyone had ever committed to writing. And he did it in poetry, while also insulting his colleagues. And while he was at it, almost as a casual aside, Brahmagupta did something even bolder. Something we are going to come back and sit with very soon. He wrote rules not just for zero, but for the numbers that lie below it. And he didn't reach for cold, abstract language to do it. He talked about fortunes and debts. A fortune was a positive amount, money in your hand. A debt was a negative amount, money that you owe. And in that warm, everyday merchant's vocabulary, he calmly described how they combine a debt taken away from nothing, he said, turns into a fortune. A fortune taken away from nothing turns into a debt. Read that again. Gently. He was doing arithmetic on the far side of zero. In that shadowy country of less than nothing. In the year 628, centuries before most of the rest of the world was anywhere near ready to admit such a country even existed. But I'm getting ahead of myself. The way Brahmagupta did. That door is for a little later, for now. Just notice that the moment you truly accept zero as a number, you have quietly opened the way to numbers, stranger still. And here is one of those moments that gives me goosebumps. The same shiver we felt in the first part of this story. Remember the Maya, on the other side of the entire planet, with no ship and no road connecting them to India. Remember their little symbol shaped like a shell, sitting in their calendars to hold an empty place. They had reached for the same idea, alone, in the jungle, in the same few centuries. It really does seem, sometimes, as if certain ideas are simply ripe, hanging low, waiting for any mind anywhere that reaches high enough. Zero was apparently one of those ideas. But the Maya thread, as we said, would stay locked in the Americas. It was Brahmagupta's zero that was about to go on a very, very long journey. Picture that journey almost like a trip across a map, taken slowly, over 500 years. First, the idea travels from India northwest into the brilliant, restless world of the medieval Islamic empires, and it lands in Baghdad, and there, in a place sometimes called the House of Wisdom, where scholars gathered to translate and absorb the knowledge of every culture they could reach. It meets a Persian mathematician named Al-Khwarizmi, who lived roughly from the year 780 to 850. He took these Indian numerals, including the zero, studied them, and wrote a clear, patient book explaining how to calculate with them. That book mattered so much that when it was later carried into Europe, his very name, worn down and Latinized over the centuries, became our word algorithm. And the title of another of his books gave us the word algebra. So every time you hear the word algorithm today, in some article about computers and your phone, you are saying a faint echo of the name of a man in 9th century Baghdad who helped carry zero west. From the Islamic world, the idea drifts across the Mediterranean and washes up on the coast of Italy. And here we meet a merchant's son, Leonardo of Pisa, better known by the nickname history gave him much later. Fibonacci. He lived from around 1170 to 1240. And as a boy, he traveled with his father, who worked as a kind of customs official, over to the bustling trading ports of North Africa. And there, surrounded by Arab merchants doing business, young Leonardo watched something that must have felt almost like magic. These traders could calculate fast, fluidly, running circles around the merchants back home. And they were doing it with this strange set of 10 little symbols, including that round nothing. In the year 1202, he wrote a book about it, the Book of Calculation, packed with practical examples for shopkeepers and bankers, all built on these new numerals. And you would think, wouldn't you, that Europe would have grabbed this gift with both hands. A faster, cleaner, more powerful way to count. Who could possibly object? Now here's the part of the story that history finds a little embarrassing. They objected, loudly, because change is frightening. And because the old Roman way of writing numbers had been good enough for 1,000 years. And because, well, this new zero made some people deeply nervous. And in the year 1299, in the city of Florence, that nervousness became law. The guild that governed the money changers, the bankers of the city, passed a rule. Their members were forbidden from using these Arabic numerals in their official account books. They had to go back to the old Roman letters, or spell the amounts out in words. The reason was fear of fraud. You see, a clumsy Roman number is hard to tamper with. But these slick new digits could be altered by a dishonest hand. At 0, with a quick stroke of the pen, could be turned into something else entirely. So the very thing that made the new numbers powerful, their smooth efficiency, was exactly what made the authorities distrust them. Sit with the irony of that for a second. The single most important number ever invented. The number that now sits silently inside every calculation that runs the modern world. Every bank balance. Every line of computer code. Every price and pixel and clock. That number was, for a stretch of time, in the most sophisticated commercial cities in Europe, literally illegal. Of course, you cannot ban a better idea forever. Merchants kept using the new numbers quietly in their private notes because they simply worked better. And slowly, over the next 2 or 3 centuries, the old Roman way faded into the thing you see only on clock faces and the names of kings. Zero won. It always was going to win. And there is something deeply satisfying to me about how it won. Not with a war, not with a decree, but by sheer usefulness. By being so quietly indispensable that in the end, nobody could remember how they had ever managed without it. There is one last thing about 0 I have to mention before we move on, because it is a small crack that will open into an enormous chasm later in our story. Even Brahmagupta, who got almost everything right, stumbled on one thing. He tried to work out what happens when you divide by 0. And he got it wrong. And the truth is, he was in good company. Because dividing by 0 is genuinely strange. Here is the gentlest way to feel it. Imagine you have a pizza, and you want to share it among some friends. Among 2 people. Easy. Everyone gets half. Among 1 person. Fine. They get the whole thing. But now try to share that pizza among 0 people. Not 1 person. 0 people. How big is each share? The question doesn't fall apart because the math is hard. It falls apart because the question itself has quietly stopped making sense. There is no answer. Because there is nothing for an answer to be about. And that little crack, that place where 0 refuses to behave, is a door we will come back and walk through much later, into the dizziness of infinity. But for now, let 0 rest. It earned it. Think about where it has been. From an empty space the Babylonians didn't trust, to a faithful little nothing holding a place in clay, to a true number that a sharp-tongued poet in India finally let breathe, to an idea that crossed half the world through Baghdad and Pisa, was feared and outlawed in Florence, and then quietly conquered everything anyway. It is the most powerful number we have. And it is the one that stands for having none of anything at all. I think that is one of the most beautiful jokes the universe ever let us in on. 0 also turns out to be a kind of hinge. A door swings on its hinge, opening one way into a room, the other way into the hall. And 0 sits at exactly that pivot point in the world of numbers. On one side of it lie all the numbers we have ever talked about. The ones for having things, 1 sheep, 2 coins, 3 stars. More and more, climbing forever upward. But if you have a number for nothing, a true number, sitting at the hinge of the door, then sooner or later somebody is going to do the obvious, slightly dangerous thing. They are going to reach for the handle and push the door the other way. They are going to ask whether there might be numbers on the far side of nothing, numbers for less than nothing at all. And the moment people took that question seriously, they walked straight off the edge of the number line into a territory that felt, to almost everyone who first encountered it, completely and utterly absurd. So, less than nothing, a number below 0. And before we go one single step further, I want to say something kind, because I suspect you might need it. If, somewhere in the back of your mind right now, a small stubborn voice is saying, "Hang on, that's ridiculous. You cannot have less than nothing," then I have genuinely lovely news for you. You are in superb company. For well over 1,000 years, some of the sharpest mathematicians who ever lived looked at the numbers below 0 and said, in effect, "No, absolutely not. Those are not real numbers. Go away." So if negatives feel a little absurd to you, that feeling is not a failure. It is an echo of one of the longest arguments in the history of thought. And I think it's worth honoring that feeling for a moment before we gently take it apart. Because the feeling is right about one thing. You truly cannot have -5 apples. Go to the fruit bowl, try to pick up -5 apples and hand them to a friend. It can't be done. There is no basket in the world that holds less than no fruit. And for a very long time, that was the whole objection. And it sounds airtight. A number is supposed to count a pile of things. There is no pile smaller than an empty one. So what could a number below empty possibly mean? Here's the quiet trick that dissolves the whole problem. Negative numbers were never really about how many things you have. They were about something else hiding underneath counting. They were about direction. Let me give you the warmest example I know. Think about money. But think about it honestly. You have 10 coins in your hand. That is a positive amount. A fortune. Something you can hold. But now imagine you owe someone 15 coins. You cannot hold a debt. You cannot stack it on the table. And yet, it is utterly real. It shapes your whole week. If you gather up everything you own, all 10 coins, and hand them over, you are still short. You are not at 0. You are below it. That gap, that 5 coins of still owing, is a negative number. And there is nothing absurd about it at all. Anyone who has ever been in debt knows exactly how real it feels. Or picture a thermometer on a cold morning. The kind with a thin line of liquid climbing up a scale. On a warm day, the line sits high. As it cools, the line sinks towards 0. And then, on a truly bitter night, it keeps right on sinking, below the 0 mark, into the cold numbers underneath. Nobody stands at the window saying that the temperature has become impossible. we just say it's below zero, and we reach for a heavier coat. Or think of an elevator in a tall building, the ground floor. The lobby is your zero. Press the button for the floors above and you rise into the positive numbers. But press the button for the parking garage and you sink into the basement, into floors that sit below the lobby, below zero. Perfectly real, perfectly easy to walk around in. So the strangeness was never in the numbers. It was in the picture we were using. The moment you stop imagining a pile of apples and start imagining a road with 2 directions, the whole mystery just quietly evaporates. And here is something that I find genuinely a little funny, in a way that says a lot about human beings. While the great scholars of Europe were busy insisting these numbers could not possibly exist, ordinary working people had been using them comfortably for more than 1,000 years. The merchants knew. The merchants always knew. You cannot run a business, lend money, track who owes what, without bumping into the idea of being in the red. The people doing the actual sums had made peace with negatives long before the people writing the theory would allow them onto the page. Let me take you to China, because this is where the written story really begins. And it begins beautifully, around 2,000 years ago, during the Han Dynasty. Chinese mathematicians compiled one of the great works of the ancient world, a book we call the 9 Chapters on the Mathematical Art. It gathered up centuries of practical problems: surveying land, sharing grain, fairly splitting taxes, the real arithmetic of running a vast country. And to do those calculations, they used little counting rods, small sticks laid out on a board to represent numbers. And here is the lovely part. They used 2 colors, red rods for the amounts you had, a surplus. Again, black rods for the amounts you lacked, a déficit, a debt. Red for what you own, black for what you owe. And they wrote down clear, calm rules for how to combine them, how a gain and a loss cancel, how 2 losses pile up. They were doing arithmetic with negative numbers, fluently, 2,000 years ago, and treating it as the most natural thing in the world. Just bookkeeping with colored sticks. No drama, no philosophy, no panic about whether less than nothing was allowed to exist. It simply was, because the granary was simply short. And remember our sharp-tongued poet from the last chapter, Brahmagupta. In India, in the year 628, remember how he wrote the rules for fortunes and debts, calmly doing arithmetic on the far side of zero. While insulting his rivals in verse, he was part of this same quiet tradition. The people who shrugged and said, "Of course, you can owe. Of course, there is less than nothing. The thermometer drops. The debt is real." So who was saying no? Mostly, it was the inheritors of the ancient Greek tradition, who loved numbers as pure, perfect, geometric things, lengths and areas you could actually draw. There was a brilliant mathematician named Diophantus. working in Alexandria around the year 250, who is sometimes called a father of algebra, and when one of his equations led him toward a negative answer, he did not marvel at it. He called it absurd, and he simply threw it out. To him, a solution below zero was not a discovery. It was a sign that you had asked a silly question. And astonishingly, that attitude held on in Europe for centuries, long after the new numerals had arrived, long after merchants were balancing books in the red across the whole continent. The theorists kept flinching through the 1500s and the 1600s. Learned men wrote about negatives with real distaste. They called them absurd numbers, fictitious numbers, false numbers, numbers that were, at best, a kind of useful fiction you tolerated on the way to a real, positive answer. Some accepted them grudgingly, others refused outright. And here is the detail that I think is almost unbearably human. Even into the 1700s, you could find respected, well-educated mathematicians writing entire books arguing that negative numbers were nonsense, that they confused students and corrupted the purity of algebra, and ought to be banished from mathematics altogether. Picture that. A learned man at his desk, with quill and candle, carefully composing an argument that a thing does not exist, while one floor below him, in the street outside, every shopkeeper and banker in the city is using that exact thing all day long without a second thought. There is something so stubborn, so endearingly, infuriatingly human about that. We will use a tool happily for 1,000 years and still argue it shouldn't be permitted. So what finally settled it? What ended the 1,000-year argument? It wasn't a brilliant proof. It wasn't some clever formula that forced everyone to surrender. It was a line. Just a line. Somebody. And the idea grew slowly through several minds in the 16 and 1700s. Finally drew the numbers out along a single straight road. You put zero in the middle. You walk to the right, and you climb through the positive numbers. 1, 2, 3. Off toward the sunrise. And then you simply turn around. You walk to the left of zero, in the other direction. And there they are, the negatives. -1, -2, -3, marching off the other way. The same road, the same even spacing, just two directions. And that little picture changed everything. Because suddenly a negative number was not a paradox, not a fiction, not an impossible pile of apples. It was just a place, a specific spot on a road, exactly as real as any other spot, that happened to lie to the left of where we started. Walking east on a road is not more real than walking west. They are simply opposite ways to travel the same path. And once you can see that, the absurd numbers stop being absurd. They sit down quietly in their places on the line, and they finally belong. I find something deeply restful about that. After all the centuries of argument, the resolution wasn't a battle won. It was a peace made. Everything that had felt impossible just got a seat on the same long bench and was welcomed. Now let your shoulders drop for a moment, because we have one more kind of number to find tonight. And it lives in a place we have walked right past without looking. It lives in the spaces between. Picture our number line again, with its evenly spaced ticks. 0, 1, 2, 3. We have been treating those whole numbers like fence posts. But look at the gaps between the posts. What lives in there? Anyone who has ever shared a pizza already knows. You cut it into slices. And now you are holding 3 slices out of 8. A piece of a whole. A number that is more than 0 and less than 1. A fraction. A number that sits between the numbers. These are the oldest numbers of all to actually use. Far older than 0 or the negatives, because the moment 2 people try to share 1 loaf of bread, they need halves. We met the very oldest evidence of this back in our first chapter, in Egypt, with a scribe named Ames and his papyrus, more than 3,500 years ago. And the Egyptians had a charming, slightly maddening habit. They almost always insisted on writing their fractions as a sum of pieces that each had a 1 on top. 1/2, 1/4, 1/7. So where we would happily write 3/4, an Egyptian scribe would write it as 1/2 plus 1/4, building the amount up out of these single, clean slices. They had one beloved exception, a special symbol just for 2/3. But otherwise, everything was assembled from unit pieces, like a wall built only from single bricks. And remember the Babylonians. With their love of the number 60, they wrote their fractions in 60ths and 60ths of 60ths, which let them be astonishingly precise. And that, by the way, is the deepest reason we still slice an hour into 60 minutes and a minute into 60 seconds, and a circle into 360 degrees. Every time you split a span of time into smaller parts, you are using a Babylonian fraction. The past is hiding inside your wristwatch. So these in-between numbers have a name. We call them the rational numbers. And I want to clear up something here, because the word fools almost everyone. Rational does not mean reasonable, or sensible, or sane. It comes from the word ratio. A rational number is simply any number you can write as a ratio. One whole number sitting over another. 1/2, 3/4, 17/5. That is all rational means. A number that is a clean ratio of whole numbers. And once you have those, the number line starts to feel almost dizzyingly full, because between any 2 fractions, you can always squeeze another one, between 1/2 and 1/3. There is room for a number in between, and between that one and the next, room for another, and another, forever. No matter how close together you zoom, the line stops looking like a fence of separate posts and starts looking like a solid, unbroken thread, packed so densely with fractions that there could not possibly be any room left over. Surely, you think, Surely now the line is full. Surely every single point on it is one of these ratios. And that is exactly what a remarkable group of people, about 2,500 years ago, came to believe with all their hearts. In a Greek colony called Croton, on the coast of southern Italy, around 500 years before the Common Era, there lived a man named Pythagoras and the strange, secretive brotherhood that gathered around him. You know his name from a rule about triangles. But to his followers, Pythagoras was far more than a mathematician. He was something close to a prophet. And what they founded was something close to a religion, with rituals and secrets and vows of silence. And at the very center of their faith was a single radiant belief about the universe. They believed that everything, all of it, the movements of the stars, the harmony of music, the structure of the cosmos itself, was built out of whole numbers and the ratios between them. To them, number was not just a tool for counting. Number was the secret language of reality. And every number that could exist was a clean ratio, a fraction, a point already sitting somewhere on that beautifully full line. They built their entire worldview on it. All is number. They said, all is ratio. And one of their own students, one of their own, was about to stumble onto something hiding in the simplest shape imaginable. A number that was not a ratio of anything. A number that could not be written as one whole number over another. No matter how clever you were, no matter how large the numbers you tried, a number that should not, by everything they believed, have been allowed to exist at all. And the legend says that when he revealed it, this discovery was so dangerous, so threatening to everything the Brotherhood held sacred, that it cost him his life. Because some numbers, it turned out, simply refused to be written as a ratio of anything. And finding the very first one did not just solve a puzzle, it shattered a worldview. So, let's step very carefully now and lower our voices a little, because we are walking into one of the oldest and strangest secrets ever kept. The kind of secret that, if the old stories are true, a person could be killed for telling. And the eerie thing, the thing that still gives me a small shiver, is that the secret was not hidden in some far-off cave or buried treasure. It was hiding inside the most ordinary shape you can imagine, a square. Let me build it with you. Slowly, in your mind. Picture a square, just a simple square. One step long on every side, one step across the bottom, one step up each side, one step along the top. Nothing could be plainer. No. Inside that square, draw a single line from one corner, straight across to the opposite corner, the diagonal. You have just cut your square neatly in half into two triangles. Easy. You could draw this with a stick in the sand. A child could draw it. And now we ask the most innocent question in the world. How long is that diagonal line? Well, the Pythagoreans had a beautiful rule for exactly this. The rule we still teach with Pythagoras' name on it. For a right-angled triangle, the longest side, squared, equals the sum of the squares of the two shorter sides. Our two short sides are each one step long. 1 times itself is 1. So the diagonal, multiplied by itself, must equal 1 plus 1, which is 2. So the length of that diagonal is the number that, when multiplied by itself, gives you exactly 2. We call it the square root of 2. And here is what mattered so much to the Brotherhood. That line is right there. You drew it. It is a real, finite length, sitting calmly on the page between two corners. It plainly has a size. So, by everything they believed, by their whole radiant faith that all is ratio, that length simply had to be a fraction. Some whole number over some other whole number. It had to be. The only question was which one. So they went looking for it, and they could not find it. And then somebody did something far more frightening than failing to find it. Somebody proved that it could never be found. That no fraction, anywhere. Not the simple ones. Not the monstrous ones with 1,000-digit numbers on the top and bottom. None of them could ever equal the square root of 2. Let me show you the heart of that proof, because it is one of the most elegant arguments human beings have ever constructed. And you do not need any mathematics to follow it. You only need to follow a chain of plain, careful steps, and feel the trap close. Suppose, just suppose, that the square root of 2 is a fraction after all. Some whole number on top, some whole number on the bottom. And let's say we have already done the obvious tidying up. We have cancelled it down as far as it will go, so that the top and bottom share no common factors. They cannot both be even. For instance, because if they were, we could cancel another 2 out of both. All right, hold that. A fraction, fully cancelled, that squares to 2. Now follow gently. If that fraction times itself is 2, then a little rearranging tells us that the top number multiplied by itself is exactly twice the bottom number multiplied by itself, and twice anything is an even number. So the top number multiplied by itself is even. But here's a quiet fact about numbers. An odd number times itself is always odd. 3 times 3 is 9. 5 times 5 is 25. Always odd. So if the top number times itself came out even, the top number itself simply has to be even. Stay with me. We are almost there, and the floor is about to drop. If the top number is even, we can write it as 2 times something. And when you square that and trace it back through, you find that the bottom number multiplied by itself must also be even, which means the bottom number is even too. And there it is. The trap. We just proved the top is even, and the bottom is even. But we began by saying we had already cancelled this fraction all the way down, that the top and bottom shared nothing in common. They cannot both be even. We assumed they weren't, and yet the logic forces them to be. the whole thing collapses in on itself. And here is the thing that must have felt to those ancient minds, like the solid floor of the universe giving way beneath their feet. This proof does not say, "We haven't found the right fraction yet." It does not say, "Keep looking. It's out there, somewhere." It says something far more total. It says no such fraction can possibly exist. Not because we are not clever enough, not because we lack the time. There is no fraction equal to the square root of 2. There never was, and there never will be. Not now, not in 1,000 years. Never. Let that single word sit in the dark for a moment. Never. You drew a line, a real, ordinary line, one corner of a square to the other. And the length of that perfectly real line is a number that lives in none of the places the Pythagoreans believed numbers could live. It is not a whole number. It is not a fraction. It is a refugee from their entire universe. And this brings us to the legend, the dark, beautiful legend. And I want to be honest with you that it is a legend, half history and half ghost story. And we truly do not know how much of it is real. But here is the tale that has come down to us across 2,500 years. They say the man who found this, or the man who let the secret slip, was named Hippasus, of a town called Metapontum, in the south of Italy. He was one of them, a Pythagorean, a member of the Brotherhood, sworn to its secrets. And the Brotherhood, faced with this number that should not exist, did not celebrate. They were horrified. This was not a fun puzzle to them. It was heresy. It meant their God. The whole numbers and their ratios did not in fact rule everything. So they decided this knowledge must never leave the inner circle. But the secret got out, and the story goes that Hippasus was the one who told it, who revealed to outsiders that the world contained these unspeakable numbers. And for that betrayal, the legend says, he was taken out onto the water, far from shore, and thrown into the sea to drown. Some versions whisper that it was not even the Brotherhood who did it, but the gods themselves, who drowned him for revealing something that was never meant to be known. Picture that for a moment, however much of it you choose to believe. A man dropped into the dark water, not for stealing, not for killing, but for telling the truth about a triangle. I think it is one of the strangest stories in all of human history. Knowledge so dangerous that a person died for it. And the knowledge was simply this: the diagonal of a square cannot be written as a fraction. There is even a lovely old word for what Hippasus found. We say two lengths are incommensurable, which means, quite literally, that they cannot be measured by a common measure. Take the side of the square and its diagonal. There is no tiny ruler, no matter how small. That fits a whole number of times into both. You can divide your ruler in half, in tenths, in millionths. And one of those two lines will always overshoot or fall short by a sliver. The two lengths share no common thread. They belong to different worlds, living side by side inside one little square. And think for a moment about what that did to those people, not as mathematicians, but as believers. They had not simply run into a hard problem. They had been told by the universe itself, in the plainest possible language, that their deepest faith was incomplete. The world was not, after all, built only out of tidy ratios. There were lengths, real and finite ones, sitting inside the simplest shapes a child could draw, that their numbers could not name and never would. It is one thing to be proven wrong about a sum. It is another thing entirely to be proven wrong about the nature of reality by a triangle you drew yourself in the sand with your own hand. I am not sure we even have a good modern word for that particular kind of vertigo. The solid ground you have trusted your whole life turning out to have a small crack in it, and through the crack, a drop that goes down forever. And once the shock settled, something remarkable happened. People did not, in the end, run away from these numbers. They learned to live with them, and even to love them. About 200 years after Pythagoras, in Alexandria, the great Euclid devoted an enormous and famously difficult portion of his masterwork, the Elements, to taming exactly these irrational lengths, putting them on solid, rigorous ground. The numbers that had once seemed like monsters were slowly welcomed in. We even gave them a home on our number line, tucked into the gaps between the fractions, in spaces so fine we never knew they were there. We call them the irrational numbers. And once again, that word does not mean crazy or unreasonable. It just means not a ratio, a number that cannot be written as one whole number over another. And if you write one out as a decimal, it does something a little hypnotic. It never ends, and it never repeats. The digits just keep unrolling, on and on, with no final digit and no looping pattern, like a story that goes forever and never reaches its last word. And the two most famous of these endless numbers are old friends you have met your whole life. One is the number we call pi, the number you get when you measure all the way around any circle and compare it to the distance straight across. It begins 3.14159, and then it simply never stops, never settles, never repeats, forever. The other we call E, a number a little over 2.7, which quietly governs how things grow, how money compounds, how populations swell, how a hot drink cools. Both of them endless, both of them unwritable in full. I find it a little funny, in the gentlest way, that a number you can never finish writing is the thing silently calculating the interest on a savings account, or the slow cooling of the tea going cold beside you right now. And here is where it turns quietly, almost unbearably beautiful to me. These two numbers are not just irrational, they are something rarer and wilder still. Something mathematicians call transcendental. Let me give you the gentlest sense of what that means. The square root of 2, wild as it is still secretly tame in one way. It is the answer to a clean little question. What number times itself gives 2? You can pin it down as the solution to a simple equation. But pi and e cannot be pinned down by any such equation at all. No matter how complicated, there is no neat algebraic question that has pi as its answer. They float entirely free of the whole machinery of algebra. They transcend it. That is what the word means. And this is not just a curiosity. Remember Archimedes, the very first person we met in this whole story. Drawing his polygons in Syracuse, he spent enormous effort squeezing pi between 2 fractions, trapping it between 22/7 and a slightly smaller number, getting closer and closer. And now we understand why he could only ever approach it and never land on it. He was chasing a number that no fraction could ever catch. There was an ancient dream that haunted geometers for over 2,000 years, called squaring the circle. The challenge was this: using only the 2 purest tools the Greeks allowed, a compass and a straight edge. Could you build a perfect square with exactly the same area as a given circle? It is a bit like being told to build a perfectly square fence enclosing exactly as much ground as a round pond, using nothing but those 2 simple instruments. People tried for 20 centuries. Kings and cranks and brilliant minds, all of them failing. And then, in the year 1882, a German mathematician named Ferdinand von Lindemann finally proved why every single one of them had failed. He proved that pi is transcendental, and because of the deep nature of those 2 simple tools, a transcendental length like pi can never be constructed with them, which meant the circle could never be squared. Not because nobody had been clever enough, but because, like Hippasus's fraction, it was forbidden by the very structure of number itself. A puzzle 2,000 years old was finally, gently, laid to rest. The answer was no. And now we knew exactly why. So sit for a moment in the strange peace of where we have arrived. We found numbers we can never finish writing down. Numbers with no last digit. That loop into no pattern. That slip through every fraction. And yet these uncatchable, unfinishable numbers are the exact numbers you need to measure a circle, or to describe how a living thing grows, or how the planets curve through space. The unwritable turns out to be the most useful. The thing the Pythagoreans feared as a monster turned out to be woven into the deepest fabric of the real world. There is something that calms me, right down to the bone, in that idea. That reality is larger than any creed we build around it, and generous enough to let us measure it anyway. So now, our number line is truly full, crowded with whole numbers and negatives, packed tight with every fraction, and threaded through, in the impossibly fine gaps between. With these endless, irrational numbers, there is no room left, not a sliver. Every single point is taken. The line is complete. Which is exactly why the next kind of number could not be found on the line at all. It had to be invented somewhere the line cannot reach, off the page entirely, in a direction no one had thought to look, a number whose square, whose own self multiplied by itself, comes out to less than nothing. a number so impossible that the very man who first stumbled onto it called it useless, and turned his back, and walked away, right before it became the secret at the heart of a Renaissance murder mystery. And, in time, the hidden language of reality itself. So here is a question that sounds, at first, like a small joke. What number, when you multiply it by itself, gives you -1? Take a moment with it, the way the people in tonight's story had to. Try a positive number. 2 times 2 is 4. Positive. Try a negative number. -2 times -2 is also 4. Still positive, because a negative times a negative comes out positive. The way 2 flips turn you back to facing forward. So a positive times itself is positive. A negative times itself is positive. And 0 times itself is just 0. There is, quite simply, no number anywhere on our beautifully full line whose square comes out below 0. It cannot be done. The line has no such number. And we just spent a whole chapter proving the line was complete. So the only sensible response, surely, is to laugh, shrug, and say, well, that number doesn't exist. And for a very long time, that is exactly what everyone said. Even the brilliant man who first wrote one of these things down looked at it, called it useless, and walked away. But I want to show you tonight how that useless little nothing turned out to be running the device in your hand, the signal carrying my voice to you, and the deepest physics we know. This might be the strangest turnaround in the whole history of numbers. And here is the part that I find genuinely wild. The part that changes everything. These impossible square roots of negative numbers did not arrive because someone sat down and tried to invent a fantasy. Nobody went looking for them. They showed up uninvited. Gate crashing. Right in the middle of people solving perfectly ordinary problems. Problems whose final answers were plain. Sensible. Everyday numbers. They were not the destination. They were a toll booth on the only road to the destination. You could not reach the real, honest answer without passing straight through the impossible one. Let me explain where they came barging in. And to do that, I have to take you into one of the soapiest, most gossip-worthy chapters in the history of mathematics. Because this is not a dry tale. This one has secrets. Betrayal. Public duels. A broken oath. And, before it's over, a beheading. Pull the blanket up. This is a good one. In Italy, in the 1500s, mathematicians did something we have completely lost today. They fought, in public, for money, and jobs, and glory. 2 scholars would each hand the other a sealed list of problems, and they would meet on an appointed day, sometimes in a packed hall, and whoever solved more of the other's problems won. Reputations and university posts hung on these duels. So if you discovered a powerful new method, you did not publish it and share it with the world. You hid it. It was your secret weapon. and you guarded it the way a great chef guards the one recipe that made him famous. And the great secret weapon of that age was a way to solve what are called cubic equations. Do not worry about the details. Just picture a certain kind of harder puzzle. One rung up the ladder from the equations everyone could already do. A puzzle that had stumped the greatest minds since antiquity. And around the year 1515, a professor in Bologna named Scipione del Ferro cracked, part of it, a real working method. And what did he do with this triumph? He told almost no one. He kept it locked away for decades. And only on his deathbed did he whisper it to a single student. Enter the hero of our story, a man named Niccolò Tartaglia, and that name is itself a small heartbreak. Tartaglia was not his birth name. It was a nickname. It means, roughly, the stammerer. When he was a boy, his town was overrun by invading soldiers, and a blade caught him across the face, leaving him with a wound so bad that for the rest of his life, his speech came out broken and halting. He grew up poor, mostly teaching himself mathematics. And he was, despite everything, dazzlingly good. And working alone, he too found the method for solving these cubics, independently, all on his own. So when Del Ferro's student challenged Tartaglia to one of those public duels, handing him 30 of these cubic problems, expecting to crush him, Tartaglia, in a burst of feverish work, solved every last one, while his challenger solved almost none of Tartaglia's. The stammering, self-taught outsider had won completely, and now he held the most coveted secret in Italian mathematics, which is where the villain, or at least the most colorful character, walks in. Girolamo Cardano. And what a piece of work this man was. A physician, a brilliant one, a mathematician, an astrologer, and a relentless, lifelong gambler who once wrote an entire book about games of chance, which makes him, almost by accident, one of the founders of the study of probability. Cardano heard about Tartaglia's miraculous formula, and he wanted it badly for a great book he was writing. So he begged, he flattered, he invited Tartaglia to his home, and finally, Tartaglia gave in and shared the secret. But only after Cardano swore a solemn oath never to publish it. And here is a lovely human touch. Tartaglia did not hand it over as a clean set of instructions. He gave it as a poem, in verse, so it could be memorized but not easily understood by anyone looking over a shoulder. For a while, Cardano kept his word. But then, working with his own astonishingly gifted student, a young man named Lodovico Ferrari, Cardano traveled to Bologna, and there he was shown Del Ferro's old private notebook, and he realized something that, to his mind, changed the rules. Tartaglia had not been the first to discover this after all. Del Ferro had it years earlier. So, Cardano reasoned, the oath no longer bound him, because the secret was not truly Tartaglia's to begin with. And in the year 1545, in his great work on algebra, Cardano published the method for all the world to see, giving credit to Del Ferro and to Tartaglia both, but publishing it all the same. Tartaglia was incandescent with rage. Betrayed, he fired off furious accusations, and the whole feud finally exploded into yet another public showdown, this time between Tartaglia and the loyal young Ferrari, who rose to defend his master. And by most accounts, it went terribly for Tartaglia. He was a deep thinker. But Ferrari was the sharper public debater. And on his home turf, Tartaglia left humiliated, his hopes of a good position in ruins. He had won the formula and lost almost everything else. And the darkness in this story does not even stop there, which is why I promised you a beheading. Cardano's own life later collapsed into tragedy worthy of an opera. His beloved son was convicted of poisoning his wife and was executed. Cardano himself was eventually imprisoned by the Inquisition for the crime of casting a horoscope of Jesus. These were not gentle men in gentle times. This new mathematics was being born in a world of real blood. But step back from all the human wreckage for a second, because there is a mathematical ghost haunting the whole affair. When you actually used this hard-won formula on certain perfectly reasonable cubic puzzles, the kind whose answers were ordinary, real numbers you could point to, the formula would, partway through, demand that you take the square root of a negative number. The impossible thing, it sat right there in the middle of the calculation, blocking the road. And the maddening part was, if you just held your nose, carried the impossible thing along as if it were a real number, and kept going, it would eventually cancel itself back out and leave you holding the correct, sensible, real answer at the end. The impossible number was a bridge. The answer was real on both banks, but the only way across the river ran straight over it. And this is where a quieter hero steps in. My favorite person in this whole tangled story, an engineer from Bologna named Raphael Bombelli. While everyone else was either ignoring these square roots of negatives or treating them as a kind of embarrassing sleight of hand, Bombelli had a thought so simple and so bold that it borders on courage. He thought, what if I stop asking whether these things are allowed to exist and just start working with them? What if I give them clear rules? Treat them as honest citizens and see if the mathematics stays consistent? He himself described it as a wild idea, almost a crazy one, but he did it. He wrote down rules for how these new numbers add and multiply. And when he put them to work, everything held together perfectly. The impossible numbers behaved. That was the turning point. Not a proof that they were real, but a decision to take them seriously and find out. And the more people did, the more astonishingly useful they became. It took a couple of centuries more to make them respectable. The great Leonhard Euler, in the 1700s, gave the square root of -1 a simple name, a single letter, I, just I. And then Carl Friedrich Gauss, one of the most powerful mathematical minds who ever lived, along with a few others working around the same time, gave these numbers something they had been missing all along: a home you could see, a picture. And the picture is so simple that I want to walk you into it slowly. Because once you see it, the word imaginary starts to feel like a cruel joke. Think about what multiplying by -1 actually does to a number on our line. Take the number 3. Sitting to the right of 0. Multiply it by -1 and it jumps to the other side, to -3. On the left, it flipped. It made a half turn, a full 180 degrees around 0, like spinning to face the opposite direction. Now here is the gorgeous question. If multiplying by -1 is a half turn, then what would be a quarter turn? What single operation, done twice in a row, would add up to that full flip? That operation is multiplying by I. The number I is not a thing on the line at all. It is a quarter turn, a 90-degree pivot, lifting you up off the line entirely, into a new direction. And that is exactly why I, multiplied by itself, gives you -1. 2 quarter turns make 1 half turn. Turn 90 degrees. Then 90 more. And you are facing backward. Which is precisely what multiplying by -1 means. The impossible number is just the direction nobody had thought to turn. So now we have a map instead of a line. The ordinary real numbers run east and west, left and right, exactly as before. And the imaginary numbers run north and south, the new direction, the quarter turn. We call this map the complex plane. And any point on it, with a real part and an imaginary part, is a complex number. We did not just find a new number, we unfolded a whole second dimension of them, sideways off the old line. A flat country of numbers where the line had only ever been a single road. And now, the part that I think is one of the most beautiful surprises in all of human knowledge. Here is what should have changed that miserable name forever. There is nothing imaginary about the number that lets your phone pick out a single voice in a noisy room. When your device takes the messy wall of sound around you and untangles it into separate voices, separate frequencies, it is doing that with complex numbers. The same mathematics carries every Wi-Fi signal through the air to you, packs every digital song, sharpens every image. The entire technology of signals runs on these supposedly fake numbers. The electricity humming in your walls, the alternating current that powers your home, is so much easier to understand through complex numbers that engineers reach for them every single day. And then there is the deepest place of all. When physicists in the 20th century went down to the tiniest scale of reality, to the behavior of atoms and particles, and wrote the equations of quantum mechanics, the equations that describe what everything is actually made of, they found that the square root of -1 was sitting right there in the heart of them. Not as a convenience, not as a trick. It appears to be woven into the basic grammar of the universe. The most fundamental description we have of physical reality is written in these impossible numbers. Let that land softly. The number people laughed at, called useless, called a fiction. The number named imaginary as an insult turns out to be one of the truest things we have ever found. It runs the machine you are holding. It may run the world itself. Which brings me to the saddest little injustice in this whole story. And I have to say something about it before we move on, because it has confused and frightened generations of students. The name, imaginary, it was coined centuries ago by a thinker who meant it dismissively, as a way of saying these numbers were not real, were a mere figure of speech, and the slur stuck. It became the permanent, official name, and I think it is one of the worst pieces of naming in the entire history of science, because there is no sense in which these numbers are more imaginary than any other. Remember, every single kind of number we have met tonight was once called impossible, or absurd, or false, by someone. Zero, the negatives, the irrationals, and now these. The number 3 is no less invented, no less a pure idea than the number I. We just got comfortable with 3 a few thousand years earlier. The truth is, they are all imaginary, and they are all completely real. And the line between those two words was never anything more than how long we'd had to get used to the idea. So pause here and feel how far we have come. We started in our first chapter with someone cutting notches into a bone, and we have arrived at a second dimension of numbers, a flat map of the impossible that quietly describes the deepest fabric of physics, from a tally on a baboon's leg to the equations of the atom. That is the journey of one idea, learning to be braver and braver about what it would allow to be called a number. And yet, for all that bravery, notice something. Every kind of number we have built tonight, no matter how strange, how negative, how irrational, how impossible, was still, in the end, just a number, a single thing, a point you could put your finger on. Nobody had yet dared to ask the question that does not ask about a single number at all, but about all of them at once. The question that breaks the very idea of size. We have talked, again and again, about lists of numbers going on forever, infinity. But here is the thought that almost nobody had the nerve to think. Is every infinity the same size? Are all the endless things equally endless? Because the answer, astonishingly, is no. Some infinities are genuinely, provably, larger than others. And the gentle, brilliant man who first proved this, who first walked into that fire, was attacked so bitterly by the mathematicians of his own day that it helped break his health. And in the end, his mind. And to follow him, we have to leave the safe, finite world entirely behind, and ask the most vertiginous question there is. How many numbers are there? Really? All of them? At once? So here we are, at the very edge of everything. We have followed numbers out of a cave, through a forbidden zero, past the absurd and the impossible, all the way out to a second dimension that runs the physics of reality. And now we are going to step off the edge of the finite world altogether and ask the question that sounds almost childish until it suddenly becomes the deepest thing you have ever considered. How big is infinity? And, stranger still, is there only one of it? Let me ease you into this very gently, because it is the most beautiful idea in this whole long night, and I do not want to rush it. First, we need to agree on what it even means for two collections of things to be the same size. And here is the lovely trick. You do not need to count them. Imagine a vast ballroom full of people and full of chairs, and you want to know if there are the same number of each. You could count both, which would take forever. Or you could simply say, "Everyone, please, find a chair and sit down." And if, at the end, every person has a seat and every seat has a person, with nobody standing and no chair empty, then you know, without ever counting, that there were exactly as many people as chairs. They pair up perfectly. That is all sameness of size really is. A perfect pairing. 1 to 1. Nothing left over. Now hold that simple idea, because we are going to carry it out past the end of the numbers. Picture the counting numbers. 1, 2, 3, and 4. Marching off forever. That is an infinite collection. And there is a famous little story that shows you how strangely infinity behaves. A story about a hotel. Imagine a hotel with infinitely many rooms, one for every counting number. And imagine it is completely full. Every single room has a guest. Now, late at night, one more tired traveler walks in and asks for a room. In a normal hotel, you would turn them away. But in this one, the clerk simply smiles. He asks every guest to move down one room. The guest in room 1 moves to room 2. Room 2 moves to room 3. And so on. Everyone shuffling along by one. And because the rooms never run out, everybody still has a room. And now room 1 sits empty, ready for the newcomer. A full hotel. And it still had space. That is your first taste of how infinity refuses to behave like an ordinary number. And it gets stranger, in a way that lulls you into a false sense of safety, because you might think, surely the fractions, all those numbers crammed densely between the whole numbers. Surely there are vastly more of those than there are plain counting numbers. And yet, with a clever enough seating plan, you can pair up every single fraction with a counting number. 1 to 1. None left over. The fractions, dense as they are exactly the same size of infinity as 1, 2, 3. They all fit in the hotel. So you begin to suspect that maybe infinity is just infinity. One single size, the biggest there is, and the only one. And this is exactly the trap that the universe had set. And the man who walked into it was named Cantor. Cantor was a mathematician working in Germany in the late 1800s. A thoughtful, sensitive, deeply original man. And he asked a question almost nobody else had the nerve to ask seriously. What about all the numbers, not just the fractions, but every number on the line, including all those endless, never-repeating irrational numbers we met earlier, the whole continuous, unbroken line. Could you fit all of those into the hotel too? Could you pair every single real number with a counting number? And what he discovered and proved, with an argument so simple and so devastating that people still teach it to teenagers, is that you cannot. There are too many. The real numbers are a bigger infinity than the counting numbers, a genuinely, provably larger endlessness. Let me show you how he proved it. Slowly. Because you can absolutely follow this. And it is one of the most elegant things a human mind has ever done. Suppose someone claims they have done it. They hand you a list, an infinitely long list, and they swear that every real number between 0 and 1 is on it somewhere, each written out as an endless string of decimal digits. First number, second number, third number, on and on forever. A complete catalogue of the continuum. Cantor says, very calmly, all right, let me build you one number that your list forgot. Here is how he does it. He goes to the very first number on your list, and he looks only at its first digit after the point. And whatever that digit is, he writes down a different digit as the first digit of a brand new number he is creating. Then he goes to the second number on your list, looks only at its second digit, and again writes down something different as the second digit of his new number. Then the third number on the list, its third digit. Change it. The fourth number, its fourth digit. Change it. He walks diagonally down through your entire infinite list, taking one digit from each number in turn, and deliberately making his new number differ from it in exactly that spot. Now look at the number he has built. Could it be the first number on your list? No, because it differs from the first number in the first digit. Could it be the second? No. It differs from the second in the second digit. Could it be the millionth number on your list? No. Because away, back at the millionth digit, he deliberately made it different. His new number cannot be anywhere on your list, because it was custom built to disagree with every single entry in at least one place. And yet it is a perfectly good real number between 0 and 1. So your supposedly complete list was missing at least one number. And the cruelest part is, you cannot fix it by just adding his number to the end, because he can simply run the trick again and build yet another one you missed, and another, forever. Stay here with me for one quiet moment, because this is the summit of our whole journey, and I want you to feel the floor of the ordinary fall away. It means the real numbers can never be put into a list. They cannot be counted, even with all of infinity to count with. There are, in the most rigorous sense the word has ever had, more real numbers than there are counting numbers. Even though there are already infinitely many counting numbers, one infinity is strictly, provably bigger than another. And then comes the thought that genuinely stops me. Every single time. Cantor did not just find one bigger infinity and stop. He found a method, a machine, for always building a bigger one. Take any infinity at all, however vast, and he could show you how to construct an infinity larger than it, and then a larger one than that, and a larger one than that, an endless tower of infinities, each one dwarfing the last, rising up and up with no ceiling, no summit, no final floor. There is no biggest infinity. The word biggest simply breaks before infinity does. Let that sit in the dark above you for a moment. Not infinity, infinities, an unending staircase of the unending. I think that might be the most vertiginous idea human beings have ever had. And I find it strangely beautiful that we are thinking it together, softly, in the dark, while you are trying to fall asleep. Now I have to tell you what it cost the man who found it, because it matters, and because he deserves to be remembered with tenderness. Cantor's ideas were so radical that the mathematical establishment of his day did not welcome them. They recoiled. The most powerful of his opponents was an older, immensely influential mathematician named Leopold Kronecker, who believed deep down that only the plain whole numbers were truly real, that everything else was a kind of human invention to be distrusted. He is the one who famously said that God made the whole numbers, and all the rest is the work of man. And Kronecker did not just disagree politely. He worked to block Cantor's career, called his work dangerous, even called him a corrupter of the young. For a sensitive man pouring his soul into the deepest ideas of his life, that sustained cruelty must have been a terrible weight. Cantor lived with a serious illness of the mind, something we would today recognize and treat with far more compassion and understanding than his own century could offer. He suffered long periods of deep depression, and in his later years he spent time being cared for in a hospital, where, sadly, he died. During the hardship of the First World War, and it is tempting to tell this as a simple tragedy, the lonely genius destroyed by his enemies. But I do not want to leave him there, because that is not where his story actually ends. Because Cantor won, completely. The ideas they called diseased became the bedrock of all modern mathematics. Within his own lifetime, the great mathematician David Hilbert rose to defend him, declaring that no one would ever drive mathematicians out of the paradise that Cantor had created for them. And he was right. Today, the mathematics of infinity that Cantor built alone, against the scorn of his peers, sits underneath nearly everything, including the logic that makes the very computers and phones we use possible. The man was broken by his time. His ideas outlived all of it. I find a deep and quiet dignity in that. So we have reached the top of the ladder of infinities. But remember the little word I asked you to hold on to. Right at the very beginning of this whole long night, the word almost. The story of almost all numbers. Because even now, even here. We have only walked one path through a forest that has many stranger trees. And I want to show you just 2 or 3 of them before we let the lights go down. One October day in 1843, an Irishman named William Rowan Hamilton was walking with his wife along a canal in Dublin, turning over a problem that had haunted him for years. He had been trying to extend those flat, 2-dimensional complex numbers into 3 dimensions, and failing for a decade. And as he crossed an old stone bridge, the answer struck him all at once, like lightning. The trick was that you needed not 3 dimensions, but 4, with not one imaginary unit, but 3 of them, woven together by a strange new rule in which the order you multiply things suddenly matters. He was so afraid that this hard-won flash of insight would vanish before he could get home, that he took out a knife, then and there, and carved the key formula into the very stone of the bridge. We call what he found the quaternions. And here is the quiet punchline of the whole story. For a long time, many people thought the quaternions were a beautiful, useless curiosity, a toy. And yet, today, that number Hamilton scratched into a bridge in 1843 is the reason a spacecraft knows how it is oriented in the blackness, and the reason the character in a video game can spin and tumble smoothly through 3-dimensional space without the picture tearing itself apart. Quaternions turned out to be the perfect language for describing rotation. The useless toy became the thing that tells the satellite and the game world which way is up. It happens again and again. In this story, the thing we call worthless is just the thing we have not yet learned to need. And there are stranger numbers still. Off in the deeper woods, there are numbers invented by a mathematician named Kurt Hensel that come with a completely different idea of what it means for 2 numbers to be close. In their world, 2 numbers are near neighbors, not when they are similar in size, but when they share the same final digits. As if you lived in a town where your closeness to someone was decided by how your names ended, rather than how tall you were. And there are the surreal numbers, dreamed up by the playful genius John Conway. A single magnificent system so vast that it contains all our ordinary numbers, and the infinities, and their opposites, the infinitely small, all of them living together in one place, the zoo. It turns out, never closes. There is no final number, no last room, no complete and finished collection of all the kinds of number there could ever be. We just keep finding new ones, or making them. Whenever we reach a place our old numbers cannot follow, which leaves us at the very end of the night with the oldest and gentlest question of all. And I am not going to answer it for you, because I do not think anyone truly can. Do we discover numbers? Or do we invent them? Are they out there? Eternal and waiting, like undiscovered countries, so that the person who first grasped 0, or the square root of 2, or infinity, was simply the first to arrive somewhere that was always there? Or do we build them, the way we build cathedrals and songs? making each new kind when we have need of it, so that they are the most beautiful thing we have ever made rather than the most beautiful thing we have ever found? I have gone back and forth my whole life. And the truth is, on a night like this, the two answers start to feel like the same answer wearing different clothes. Because think of the single thread we have followed. The same quiet idea of number that let someone tally the days by carving lines into a piece of bone. 40,000 years ago in the African dusk is the same idea that became a forbidden zero, and an absurd debt, and a length that could not be written and may have cost a man his life, and an impossible square root that now hums inside every device you own, and finally a tower of infinities with no top, one unbroken thread, from a notch in a baboon's leg to the cold, clear light of the transfinite, the whole vast cathedral of number. And it started with a single human being who simply wanted to remember how many. And it is not finished. That is the last thing I want to leave you with. As your eyes get heavy, somewhere out there tonight, in some quiet room, someone is reaching for a number that does not have a name yet. A new kind that none of us have met. The person in the cave did not know they were beginning any of this. They just made a mark, and we do not get to see how it ends. Because it does not end. The counting goes on without us, far past this night and every night. And maybe that is the most comforting thought of all. You do not have to finish it. Nobody does. The great long count has been running for 40,000 years, and it will keep right on running while you sleep. Patient and endless and kind. So let it. Let the numbers go on without you for a while. You have come all the way from a notch on a bone to the edge of infinity tonight. And that is far enough. You can rest now. Let go. And drift. And let the counting carry on quietly in the dark. The way it always has. The way it always will. Good night.